Good morning to all. I am Dr. Thayalan from Radiologic Physics Foundation. Today we are going to talk about interaction of radiation with matter part 2, especially photoelectric effect. Last episode we discussed about Compton scattering. Just to repeat, what is the advantages of interaction of X and gamma rays? The interaction is very much useful to understand the biological effect that manifests in the human body. It also tells us how radiation is attenuated in a medium. In general, X-rays and gamma rays having a wavelength in the order of nanometer. 1 nanometer is 10 power minus 9 meter. They travels in the medium as wave and interact as particles. They preferably interact with the structures that are similar in size to their wavelength. That means any structure having a nanometer dimension will have actually more probability with the X-ray interactions. Therefore, the most common targets are electron, nucleus and atoms. What are the various type of interactions? Compton scattering, photoelectric effect, pair production, coherent scattering, photo disintegration. Only 5 interactions are there. These 3 interactions are very important for medical applications. These 2 has actually no significance in medical applications. So let us discuss about the photoelectric effect. Let us consider an atom. If a X-ray photon with the energy EI comes and interact with the K shell electron like this, then what will happen? The electron is removed from the atom and the removed electron is called photoelectron. As a result, positive ion is formed. Since the atom loses electron, it is simply ionized, so it is said to be actually positive ion. So if you equate the energy of the incident electron is equal to sum of the binding energy as well as the kinetic energy of the electron. So EB is the binding energy of the K shell, EKE is the kinetic energy of the photoelectron. Suppose if you want to calculate what is the energy of the photoelectron here, the energy of the photoelectron is equal to instant photon energy minus the binding energy of the electron. So the photoelectric effect is a total energy absorption. So whatever the energy the instant X-ray has, it is totally absorbed in the medium. All instant photon energy is transferred to the electron in the photoelectric effect. The photon interaction is most likely in K shell because the K shell is tightly bound. Less often L shell interaction may take place. What is the condition for photoelectric effect? The instant electron energy E is equal to or greater than the binding energy of the atom. The atom is said to be ionized as there is a vacancy in the orbit. So mostly tightly bound electron is greater than the probability of photoelectric effect. Let us see how actually the characteristic X-rays are produced in the photoelectric effect. Once there is a vacancy, this vacancy is filled by the electron of lower binding energy from higher orbit. This will create cascade of electron transition event from outer orbit to inner orbit. The difference in binding energy is released as characteristic X-rays. Sometimes the characteristic X-rays may interact with the electron in the same atom and may release the electron. Such electron release is called Auger electron after the scientist name Auger. So what is Auger electron? Auger electron is an outer shell electron with binding energy less than the energy difference of the electron transition. So this figure, let us see the iodine 131 atom, how the characteristic X-rays are produced. Let us consider the shells K, L, M like that. The K shell binding energy is 34, L shell binding energy is 5 kilo electron volt, M shell is 0.6, N shell is 0 like that. Suppose if the instant photon comes and interact with this K shell and remove this electron as photoelectron, there is a vacancy in the K shell. This vacancy can be filled from the L shell. The transition between L to K, what will happen? 34 minus 5, it is 29 kilo electron volt, which comes as in the path C. The vacancy in the L shell is filled with the M shell. What is the difference between the 5 and 0.6? 4.4 kilo electron volt. It appears as B. So this vacancy M is actually filled with the N. What is the difference between 0 and 0.6? 0.6 kilo electron volt. It appears as A. Therefore, if we compare the wavelength of all the three, lambda 4 will have the highest wavelength compared to lambda 3, lambda 2 and lambda 1, or the energy here the energy is higher, here the energy is little less, here little less and little less like that. The characteristic X-ray energy is higher in high Z material compared to low Z. That is the reason the characteristic X-rays of barium and iodine are high and they are so energetic, they leave the patient immediately after the interactions. As contrast, the characteristic X-rays of soft tissue is low energy because low Z, around 1 kilo electron volt. It is immediately absorbed in the patient itself. Let us discuss about what is cage. The probability of photoelectric interaction is a function of X-ray energy, atomic number and mass density of a medium. The probability of photoelectric effect is proportional to the atomic number cubed and inversely proportional to the energy to the power of 3. Therefore, as atomic number increases, the probability of photoelectric effect increases. As the energy increases, the probability of photoelectric effect decreases. So, as X-ray photon energy increases, the probability of photoelectric effect decreases, resulting decreased subject contrast. So, one can draw a graph between photon energy versus photoelectric mass attenuation coefficient. You can take X-ray energy in the x-axis, mass attenuation coefficient in the y-axis, you can draw a graph. Now, if you draw a graph, then what we can observe, the attenuation decreases exponentially as the energy increases. Suppose the energy increases here, the attenuation decreases like that. But there is a discontinuity here. Why there is a discontinuity in the graph? If the photon energy is equal or greater than the K shell binding energy, the absorption increases sharply. The curve appears with discontinuities. So, whenever the energy is equivalent to K shell energy, binding energy, then there is a sharp absorption of energy in the atom. This is called K edge absorption. K stands for K shell. Now, let us see some of the K edge absorption energy of the various material. For lead, K edge absorption is 88 kilo electron volt. For barium, it is 37.4 kilo electron volt. Iodine, it is 33.2 kilo electron volt. Let us also see some of the element which we have in our human body. For oxygen, the K edge is 0.5 kilo electron volt. Calcium, it is actually 4 kilo electron volt. If you see in the graph, as the atomic number increases, the K edge value increases. So, in summary, the photon energy corresponds to K edge absorption increases with the atomic number Z. Higher the Z, greater the binding energy, greater is the photon energy at which it occurs. Thus, absorption edges of hydrogen, carbon, nitrogen and oxygen in soft tissue is less than 1 kilo electron volt since their Z is very low. Now, what is the use of actually the absorption edge concept? The absorption edge principle is very much important in selecting the X-ray filter material like aluminum and copper, as well as to select the contrast media for the different diagnostic procedures. As a take-home message, photoelectric effect dominate at energies just above K edge of the observer. Let us see the relationship between photoelectric effect and atomic number. As the atomic number increases, photoelectric effect increases, resulting higher subject contrast. For example, barium atomic number 56, iodine atomic number 53 provide higher subject contrast and used as contrast agent. Suppose if you take in the human body, the fat atomic number is 6.3, soft tissue 7.4, lung is 7.4, bone is 13.8 and air is 7.4. So among the human body material, the lowest atomic number is soft tissue, the highest is the bone. So bone gives actually higher subject contrast than soft tissue because of the high atomic number. Let us see the relationship between photoelectric effect and mass density. Photoelectric effect interaction depends on mass density of the tissue also. What is mass density? It is a quantity of matter per unit volume expressed in kilo per meter cubed. Let us see the mass density values of different material. For air, the mass density is 1.3 kilometer cubed, lung 320, fat 910, soft tissue muscle 1000, bone 1850. Let us try to take the ratio of the mass density of soft tissue and air. If you take the mass density ratio of soft tissue and air, it is 1000 divided by 1.3, around 77. If you take the soft tissue and lung ratio of mass density, it is 1000 divided by 320, it is around 3. So in terms of mass density, the air and lung actually differs, even though the atomic number is actually almost same. You can see here the soft tissue and air, the atomic number is almost same lung, but the mass density difference is very, very different. That is the reason why, though the atomic number difference is little between the soft tissue and lung, mass density difference is much higher. This is the reason why lung imaging is possible in diagnostic radiology. So as a take home message, though atomic number difference is actually less or equal, mass density difference contribute to diagnostic imaging. What are the applications of photoelectric effect? Photoelectric effect is more important than Compton scattering and high Z material and low photon energy. In contrast, Compton scattering is important low Z material and high photon energy. Both are equal and important at 30 kilo electron volt for air, water and soft tissue, 50 kilo electron volt for aluminum and bone, 300 kilo electron volt for barium and iodine, 500 kilo electron volt for lead. In diagnostic radiology, photoelectric effect dominate at contrast media and film material. Compton is dominant in air, water and soft tissue. Both are important in bone. So photoelectric effect is important in high Z material and photon energy just above the cage. In summary, photoelectric interaction occurs between bound electrons and incident X-ray photon. It is a total energy absorption. Photoelectric effect follows with the characteristic X-rays at Auger electron. Its probability is maximum if the photon has just sufficient energy equal or greater than the binding energy of the cation electron. Photoelectric cross section varies with Z to the power of 3 and inversely to the energy to the power of 3. Coefficient for the electron also varies with high Z, low Z. In high Z it is Z to the power of 3, in low Z it is actually Z to the power of 3.8. Photoelectric effect is very important, less than 50 kilo electron volt energy, especially in diagnostic radiology. I hope you enjoyed the video. We come back with another title in the next episode. Kindly subscribe and succeed. Thank you very much.